Right now, the Mars HiRISE camera is observing interstellar comet 3I Atlas as a faint dark smudge against the stellar background, which contradicts the crystal-sharp images amateur astronomers are capturing with telescopes a fraction of NASA's budget, leaving scientists unsettled. After a week-long government shutdown, NASA held an emergency press conference on November 19th and dumped image frames from 4 separate spacecraft. HiRISE from Mars orbit, showing a barely visible spot. MAVEN capturing the ultraviolet coma with hydrogen emissions on October 9th. Lucy mission frames from September, and SOHO observations from October. Each image is blurred beyond what mission specifications should permit. NASA's explanation sounds defensive. The object is dim, yes, and millions of kilometers distant, racing at 246,000 kilometers per hour at perihelion on October 30th. But amateurs with 8-inch backyard telescopes are resolving powerful jet structures, a dust anti-tail stretching 500,000 kilometers toward the sun, and an ion tail extending more than 2.3 million kilometers into deep space. That disparity is not trivial. It raises a question NASA did not answer convincingly. Why are billion-dollar space instruments delivering images worse than what a hobbyist in suburban Arizona can achieve on a clear night? The comet, designated 3I Atlas, is the third confirmed interstellar visitor ever detected. It arrived from beyond the solar system on a hyperbolic trajectory, traveling at 33 kilometers per second relative to the Sun. Discovery came on July 1st from the Atlas Survey Telescope in Chile. It reached perihelion, the closest point to the Sun, on October 30th at 1.4 astronomical units, roughly 210 million kilometers out, well beyond Earth's orbit. As of mid-November, it sits at 155 astronomical units, visible in the constellation Virgo during morning hours, shining at magnitude 9.5 to 10.8, faint but accessible to experienced observers. The nucleus is estimated between 0.4 and 5.6 kilometers across, a size range so broad it reflects deep uncertainty about what exactly is out there. What should not be uncertain, however, is image quality from spacecraft designed explicitly to observe faint, distant objects. Yet here the images are grainy, pixelated, almost deliberately unhelpful. Here's where it gets interesting. NASA's official narrative frames 3I Atlas as exotic but natural, a comet born in another star system billions of years before the Sun formed, carrying chemical signatures from an alien stellar nursery. The agency acknowledges anomalies, but downplays them with metaphors. During the press conference, one mission scientist compared the comet to coffee from different regions. Flavors vary, chemistry shifts, nothing alarming. The tone was calibrated to reassure, but the anomalies are stacking up in ways that resist easy dismissal. The comet's composition shows carbon dioxide levels far higher than typical solar system comets. Nickel content 10 times the solar abundance, water levels unexpectedly low, and a cyanogen, or CN emission anomaly that spectroscopy cannot yet explain. The nucleus has not fractured despite passing close to the Sun, a stress test that shatters most long-period comets into rubble. Brightness fluctuates unpredictably. The tail is weak compared to comparable objects. And then there is the trajectory. Here's the problem. The comet exhibits zero non-gravitational acceleration in the plane perpendicular to its orbit, designated A3 in orbital mechanics. Non-gravitational forces, primarily outgassing jets, normally nudge comets slightly off their predicted paths. Every active comet ever studied shows this effect. 3I Atlas does not. It flies as if on rails, deviating only along the radial vector pointing toward or away from the Sun, with no sideways drift whatsoever. That radial-only behavior matches what one would expect from a symmetrically venting sphere or a controlled thrust system, not a tumbling, irregular ice and rock body spinning every 16 hours. The jets themselves are another puzzle. High-resolution ground-based images reveal narrow, collimated streams of gas and dust aimed directly at the sun, not spraying randomly from the nucleus, as sublimation physics would predict. Comets rotate, sometimes chaotically, smearing jet emissions across the sky. 3i Atlas shows no such smearing. The jets hold their orientation. That is not how natural outgassing behaves. Stop and consider that. A 16-hour rotation period should cause visible changes in jet direction over the course of a single night's observation. Astrophotographers monitoring the comet nightly report stable jet morphology. Murata's image from November 16th, widely circulated on social media, shows exquisite detail. Sharp jets, a well-defined coma, dual tail structures stretching across the frame. The image was taken with amateur equipment. NASA's multi-million-dollar spacecraft, meanwhile, delivered smudges. The discrepancy fuels suspicion not just among fringe commentators, but among credentialed scientists who wonder aloud whether image release policies are being influenced by factors beyond technical limitations. Conspiracy theories thrive in the gap between official explanations and observable reality. When the explanation does not fit the data, people fill the void with speculation. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and former chair of the astronomy department, is not a conspiracy theorist. He is, however, furious. At the November 19-20 press conference, Loeb challenged NASA's narrative with a precision that left mission officials visibly uncomfortable. He enumerated more than 12 deviations from expected comet behavior, each one individually explainable perhaps, but collectively forming a pattern that demands consideration of alternatives. Loeb has spent years arguing that the scientific community dismisses the possibility of extraterrestrial technology too reflexively, applying a standard of proof for artificial origin far more stringent than for natural phenomena. With 3i Atlas, he sees vindication. The sun-directed jets are not an optical illusion, he insists. The zero transverse acceleration is not a fluke of measurement error. The structural integrity near perihelion is not a coincidence. The nickel-rich surface composition, detected via spectroscopy, is not a minor curiosity. Taken together, Loeb argues, these anomalies point toward a probability of artificial origin around 40%. That number is not a wild guess. It is Loeb's assessment based on Bayesian inference, weighing the likelihood of the observed data under natural versus artificial hypotheses. NASA predictably disagrees. Officials at the press conference emphasized that interstellar objects carry no obligation to resemble solar system analogs. Different formation environments produce different chemical fingerprints, different structural properties, different outgassing behaviors. The agency insists that every anomaly attributed to 3i Atlas can be explained within the framework of natural astrophysics, given sufficient creativity and patience. The high nickel content might indicate formation in a supernova-enriched region of a distant molecular cloud. The low water content might reflect formation beyond the snowline in a planetary system with unusual volatile distribution. The 0A3 acceleration might result from perfectly balanced outgassing on opposite hemispheres, a rare configuration, but not physically impossible. The sun-directed jets might be an artifact of nucleus orientation, coincidentally aligned during the observation window. Each explanation, in isolation, holds some plausibility, but stringing them together into a coherent natural narrative requires invoking coincidence after coincidence. At some point, the cumulative improbability of the natural explanation begins to rival the improbability of the artificial one. Read between the lines of NASA's press release. The language is carefully hedged. The comet is described as consistent with natural origin, rather than definitively natural. The anomalies are under investigation, rather than resolved. The call for additional observations is framed as routine science, but the urgency behind it suggests something more. Loeb is demanding data from the Hubble Space Telescope and the James Webb Space Telescope when 3I Atlas makes its closest approach to Earth on December 19th, reaching 1.8 astronomical units, roughly 270 million kilometers away. That is no danger to the planet far beyond the Moon's orbit, but close enough for the most sensitive instruments ever built to resolve surface features, measure thermal emissions, and analyze spectral lines with unprecedented precision. If the comet is natural, JWST's infrared spectrograph should detect water ice, silicate dust, organic molecules in ratios consistent with interstellar chemistry. If it is something else, the spectrum will not match. Loeb knows this. NASA knows this. December 19th is circled on every relevant calendar. Think about what that means. If JWST observations reveal a surface composition inconsistent with any known class of comet, if thermal imaging shows heat distribution incompatible with solar heating alone, if high-resolution imaging resolves geometric structures too regular to be erosion features, the paradigm shifts. Not gradually, not with careful academic debate, but immediately and irrevocably. The discovery of extraterrestrial technology, even defunct technology, even a fragment of an ancient civilization's detritus drifting through interstellar space, rewrites human history. It answers the Fermi paradox. It confirms we are not alone. It raises 1,000 new questions. Where did it come from? Who built it? How long has it been traveling? Are there others? Is anyone still out there? The implications cascade through astronomy, biology, philosophy, theology, geopolitics. And if the observations reveal nothing unusual, if the spectrum is mundane, the trajectory explicable, the structure unremarkable, then Loeb's 40% drops to near zero, and the scientific community breathes easier, reassured that the universe still makes sense. But the universe does not always make sense, at least not on first inspection. History is littered with observations that defied explanation until the framework expanded. Pulsars were briefly called LGM-1, Little Green Men, because their regular radio pulses seemed too precise to be natural. Quasars baffled astronomers for years until redshift measurements revealed their extragalactic distances, and supermassive black holes emerged as the power source. Fast radio bursts remained mysterious until dedicated surveys linked them to magnetaires and neutron star mergers. In each case, the initial data seemed to violate known physics, prompting speculation about artificial sources, until deeper investigation uncovered natural mechanisms more exotic than anyone had imagined. The question is whether 3I Atlas follows that pattern or breaks it. Is this another case where nature proves stranger than we thought? Or is this the case where nature finally yields to something beyond itself? Now about the data. The comet's trajectory is hyperbolic, meaning it is not gravitationally bound to the Sun. It arrived from interstellar space and will return to interstellar space, a visitor passing through, not a permanent resident. The orbital eccentricity exceeds 1, the defining criterion for an unbound orbit. The incoming velocity at infinite distance, adjusted for the Sun's gravity, is 33 kilometers per second, roughly 74,000 miles per hour, fast by terrestrial standards but unremarkable for interstellar space. The orbit's inclination is moderately steep, enough to distinguish it from the ecliptic plane where most solar system objects circulate, but not so extreme as to suggest a random trajectory through the galaxy. The comet entered from a direction roughly aligned with the galactic plane, consistent with an origin in the local stellar neighborhood, within a few hundred light years, not from the depths of intergalactic space. Perihelion occurred on October 30th at 1.4 astronomical units. For comparison, Earth orbits at 1 astronomical unit, Mars at 1.5. The comet passed between the two planets' orbits, close enough to feel significant solar radiation, but not close enough for extreme heating. Typical comets that venture inside Mercury's orbit, less than 0.4 astronomical units, experience temperatures exceeding 400 degrees Celsius, enough to vaporize volatiles and fracture weak nuclei. 3I Atlas never faced that stress. Its perihelion distance is gentle by sun-grazing standards, yet its behavior is unusual. The lack of fragmentation is notable, but not definitive. Some comets are structurally robust, monolithic chunks of primordial ice and rock compressed in the outer reaches of their birth systems. Others are rubble piles, loosely bound aggregates that shatter at the slightest perturbation. Without direct sampling, determining which category applies is guesswork. The closest approach to Mars occurred in September, exact dates still being refined as orbital solutions improve with additional tracking data. Mars orbiting spacecraft, including HiRISE, MAVEN, and the Trace Gas Orbiter, had a unique opportunity to observe an interstellar object at relatively close range, certainly closer than Earth-based telescopes could manage. HiRISE, the High-Resolution Imaging Science Experiment, is the most powerful camera ever sent to another planet, capable of resolving features smaller than a meter on the Martian surface from orbit. Pointed at 3I Atlas, it produced a dark spot on a grainy frame. MAVEN, the Mars Atmosphere and Volatile Evolution mission, detected ultraviolet emissions from the coma on October 9th, confirming hydrogen outgassing, consistent with water sublimation or other hydrogen-bearing volatiles. Lucy, a NASA mission en route to Jupiter's Trojan asteroids, captured images in September as the comet crossed its field of view. SOHO, the Solar and Heliospheric Observatory, stationed at the Earth-Sun Lagrange point, added observations in October. Each dataset is valuable. None is spectacular. The collective image quality is, to put it charitably, disappointing. Here's where things get strange. Amateur astrophotographers are not constrained by mission parameters, spacecraft pointing limitations, or data transmission bottlenecks. They point their telescopes at the comet night after night, stacking exposures, tweaking processing algorithms, sharing results online. The images they produce are stunning. The anti-tail, a narrow spike of dust pointing toward the sun, stretches 500,000 kilometers, roughly 1 1/3 times the Earth-Moon distance. That structure forms when larger dust grains, ejected from the nucleus during previous outgassing events, lag behind the comet in its orbit, creating a trail that from Earth's perspective appears to point sunward. The ion tail, driven by the solar wind, extends more than 2.3 million kilometers, 6 times the Earth-Moon distance, a delicate filament of ionized gas glowing in the ultraviolet and visible spectrum. These features are resolved in backyard images. NASA's spacecraft, with optics and sensors designed to study faint, distant phenomena, deliver blurs. The official explanation cites technical constraints. Spacecraft cameras are optimized for specific targets, planets, asteroids, solar corona, not fast-moving interstellar comets. Pointing accuracy, exposure time, transmission bandwidth all impose limitations. Fair enough. But those limitations should not produce images inferior to ground-based amateur equipment by such a wide margin. The discrepancy suggests either the spacecraft observations were poorly planned, executed during suboptimal conditions, or the released images are not representative of the full dataset. The third possibility is the one that fuels conspiracy theories. If NASA possesses higher resolution images but chooses not to release them, the reason matters. Institutional caution, peer review delays, calibration uncertainties, all are plausible and mundane. Deliberate obfuscation to conceal an uncomfortable truth is less plausible but impossible to disprove without access to the raw data. Loeb raised this point explicitly during the press conference. He demanded transparency. He called for the release of unprocessed telemetry, calibration files, observation logs, everything necessary for independent verification. NASA officials responded with assurances that data will be made public, following standard archival procedures. Typically within months of acquisition, Loeb countered that months is too long when the object is receding at 33 kilometers per second, growing fainter by the day, slipping beyond the reach of follow-up observations. The window for definitive characterization is closing. JWST observations in mid-December might be the last chance to resolve key questions before 3I Atlas fades into the darkness between stars. The chemical composition adds another layer of complexity. Spectroscopy reveals unusually high carbon dioxide, CO2, emission relative to water. Most solar system comets are water-dominated, with CO2 as a minor component. 3I Atlas inverts that ratio. One explanation is formation in a colder, more carbon-rich protoplanetary disk, perhaps around a star with different metallicity than the Sun. Another explanation is preferential loss of water over billions of years of exposure to cosmic rays and interstellar radiation. Water ice, even at cryogenic temperatures, can sublimate slowly in the vacuum of space. CO2 ice is more stable under certain conditions. A comet adrift for 1 billion years might lose its water mantle, leaving a CO2-rich core. Plausible, but speculative. The nickel detection is harder to explain. Spectral lines indicating nickel in the coma appear at intensities 10 times higher than solar abundance. Nickel is a heavy element, forged in the cores of massive stars and scattered by supernova explosions. Its presence in comets is expected, trace amounts locked in silicate grains and metallic inclusions. But 10 times solar abundance suggests the parent body formed in an environment heavily contaminated by supernova ejecta, a young stellar nursery perhaps, where massive stars lived fast and died violently, seeding the gas cloud with freshly synthesized metals. Or it suggests the nucleus has a nickel-rich surface layer, possibly a metallic shell, exposed by erosion or impact. Loeb favors the latter interpretation. A metallic shell is not natural for a comet. It is, however, consistent with a manufactured object, a probe or fragment of one, coated in metal for thermal protection or structural integrity. The CN anomaly complicates the picture further. Cyanogen, a molecule of carbon and nitrogen, appears in comet spectra when ultraviolet sunlight breaks down organic compounds in the coma. The intensity and spatial distribution of CN emission usually correlate with other volatiles like water and carbon monoxide. In 3I Atlas, the CN emission pattern is irregular, patchy, concentrated in regions that do not align with the brightest parts of the coma. That irregularity might indicate heterogeneous composition, pockets of organic-rich material embedded in an otherwise depleted matrix, or it might indicate localized outgassing, gas vents opening and closing as the nucleus rotates, exposing different surface areas to sunlight. Without spatially resolved spectroscopy, impossible to obtain from Earth at this distance, distinguishing between these scenarios is difficult. The 16-hour periodicity, detected photometrically as brightness variations repeating every 16 hours, is interpreted as the nucleus rotation period. That duration is neither unusually fast nor unusually slow for a small body. But paired with the stable jet orientation, it creates a paradox. If the nucleus spins every 16 hours, the jets should sweep across the sky like lighthouse beams, visible from Earth at different angles as rotation changes the perspective. They do not. They point sunward, consistently, night after night. The only way to reconcile stable jets with rotation is to propose that the active regions, the spots on the surface where gas and dust erupt, are located at the rotational poles. If the spin axis points nearly toward or away from the Sun, the poles do not change their orientation relative to the Sun as the body rotates, and jets emanating from the poles would remain fixed in direction. That geometric alignment is possible, but again, it is a coincidence. Another item added to the list. The trajectory's lack of transverse non-gravitational acceleration is perhaps the single most striking datum. When comets outgas, the escaping material exerts a rocket effect, a tiny thrust that alters the orbit. The magnitude and direction of this thrust depend on where the gas vents are located on the surface and how the nucleus is spinning. For a randomly shaped, randomly oriented, randomly rotating comet, the net thrust has components in all directions: radial, tangential, and perpendicular to the orbital plane. Those components shift the orbit's semi-major axis, eccentricity, inclination in measurable ways. Orbital analysts track these shifts to infer outgassing patterns and spin states. 3I Atlas shows a radial non-gravitational acceleration, A1 in the standard notation, consistent with gas pushing away from or toward the Sun. It shows zero tangential acceleration, A2, and zero out-of-plane acceleration, A3. Zero, not small, not noisy, but statistically indistinguishable from zero within measurement precision. That precision is not trivial. The comet has been tracked for months by professional surveys and amateur observers worldwide, accumulating hundreds of astrometric positions. Orbital solutions derived from those positions have uncertainties measured in kilometers, over distances of hundreds of millions of kilometers, precision sufficient to detect non-gravitational forces, orders of magnitude smaller than the Sun's gravity. A3 equals zero within those uncertainties. For comparison, every other well-studied comet shows non-zero A3, sometimes positive, sometimes negative, but never zero. The standard interpretation is that outgassing is inherently asymmetric, and asymmetry in three-dimensional space generically produces forces in all three dimensions. 3I Atlas violates that expectation. Loeb interprets the zero A3 as evidence of perfect symmetry, either a spherical nucleus with uniformly distributed vents or a controlled propulsion system compensating for asymmetries. NASA interprets it as a fluke, unlikely but not impossible, a statistical edge case that will be understood better with more data. The lack of fragmentation near perihelion is another anomaly in a catalog of anomalies. Comets are fragile. Sun-grazing comets, those passing within a solar radius of the Sun's surface, often disintegrate spectacularly, torn apart by tidal forces and thermal stress. Even comets passing at safer distances sometimes split, shedding chunks that drift apart over subsequent orbits. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before colliding with Jupiter in 1994. Comet Linear disintegrated in 2000 as it approached the Sun. Comet Ison vaporized at perihelion in 2013. Structural failure is common. 3I Atlas passed perihelion intact, no fragments detected, no sudden brightening that would signal a breakup releasing buried volatiles. That resilience suggests either unusual structural strength or unusual composition, perhaps more rock than ice. A dormant comet reactivated by solar heating after eons of freezing in interstellar space. But dormant comets do not produce 2.3 million kilometer ion tails. They do not sustain collimated jets. They do not outgas symmetrically enough to zero out transverse accelerations. The more one examines the details, the more the natural comet hypothesis strains under the weight of exceptions. Loeb's artificial hypothesis offers a simpler fit to the data, fewer coincidences required, but at the cost of invoking an explanation with zero prior examples, no confirmed cases of extraterrestrial technology ever detected. The Bayesian prior for artificial origin is vanishingly small, though not zero. Loeb argues that the data are strong enough to overcome that prior, raising the posterior probability to 40%. Critics argue that 40% is absurdly high, that Loeb is inflating the improbability of natural explanations and underestimating the flexibility of astrophysical theory. The debate is not resolvable with current data. December's JWST observations might settle it. The broader implications loom large. If 3I Atlas is artificial, its origin becomes the next question. The comet's trajectory, traced backward through the galaxy, does not point unambiguously to any nearby star system. Proper motion reconstructions, accounting for the sun's and the object's motion through the local stellar neighborhood, suggest an origin somewhere within a few hundred light-years, but the uncertainty envelope is wide. Dozens of stars fall within the possible source region. None are obvious candidates for hosting technological civilizations. Most are red dwarfs, small, cool, long-lived, but tidally locking their planets in configurations hostile to life as we understand it. A few are sun-like, G-type stars, stable and middle-aged, but showing no signs of unusual activity, no megastructures, no radio signals, no optical beacons. If 3I Atlas is a probe, it is an old one, ancient, possibly predating human civilization, possibly predating humanity itself, a relic from a species that rose, explored, and perhaps vanished long before Homo sapiens emerged. That narrative has a melancholic appeal. The galaxy is old, 13.6 billion years, filled with hundreds of billions of stars, trillions of planets, countless opportunities for life to arise, evolve, reach intelligence, develop technology, spread outward. The Fermi paradox asks where everyone is. One answer is that they came and went, that civilizations are ephemeral on cosmological timescales, that the galaxy is haunted by the remnants of species that burned bright and faded, leaving behind only wreckage and silence. 3I Atlas might be such a remnant, a derelict probe launched 1 billion years ago by a civilization that no longer exists, drifting powerless through interstellar space until chance brought it close to our sun and human telescopes noticed it. If true, the discovery is monumental but also sobering. It proves intelligence is not unique to Earth, but it also suggests intelligence does not endure. Alternatively, 3I Atlas might be active, still functional, still transmitting data, still executing a mission programmed eons ago. Its trajectory brought it close to Mars, closer than to Earth, in September. Did it observe Mars? Did it detect the presence of spacecraft in Martian orbit, rovers on the surface, signs of technological activity? If it is designed to recognize such signs, did it note them, store them, prepare to relay them elsewhere? The comet is now outbound, accelerating as it falls away from the sun's gravity well, heading back into interstellar space at 33 kilometers per second. At that speed, it will cover 1 light-year in roughly 9,000 years, a glacial pace by the standards of interstellar travel, but sufficient to traverse the galaxy over hundreds of millions of years. If it is transmitting, the signal would be faint, tightly beamed perhaps, aimed at a receiver no one on Earth knows how to locate. SETI, the search for extraterrestrial intelligence, has monitored the comet's position for radio emissions. So far, nothing detected. But absence of evidence is not evidence of absence, especially if the transmission frequency or modulation scheme is unfamiliar. The technological implications are profound. If 3I Atlas is artificial, its propulsion system, power source, materials, all represent technologies developed by a non-human intelligence, possibly in a physical and chemical environment different from Earth's. Studying those technologies, even as relics, even in fragments, could leapfrog human engineering by centuries. The nickel-rich surface, if it is indeed a metallic coating, might employ alloys unknown to terrestrial metallurgy, optimized for interstellar conditions where temperatures fluctuate between near absolute zero in the shadows and hundreds of degrees in direct starlight, where micrometeorite impacts and cosmic radiation erode surfaces over millions of years. The structural integrity that prevented fragmentation at perihelion might rely on bonding mechanisms, crystalline lattices, composite materials beyond current material science. The propulsion system that maintained a zero A3 trajectory, if it exists, might operate on principles physics has yet to formalize, perhaps exploiting quantum effects, electromagnetic interactions with the interplanetary medium, or manipulating space-time geometry in ways general relativity permits but human technology cannot achieve. Or it might be simpler. It might be a solar sail, a thin reflective sheet pushed by sunlight, oriented to produce radial thrust without transverse components. Solar sails have been proposed and tested in concept by human space agencies, using the pressure of photons to accelerate spacecraft without propellant. A sufficiently large, sufficiently well-controlled sail could, in principle, explain the A3 equals 0 observation. But solar sails are visible, bright, reflective, and 3I Atlas does not appear bright or reflective in the optical spectrum. Its albedo, the fraction of sunlight it reflects, is low, consistent with a dark, carbon-rich surface, not a shiny metal or polymer film. Spectroscopy shows absorption features, not the featureless reflection spectrum a sail would produce. The solar sail hypothesis does not fit the data either. The political and cultural implications are harder to quantify, but no less significant. If definitive proof of extraterrestrial technology emerges, governments face decisions about disclosure, public messaging, resource allocation. Does the discovery justify increased funding for space exploration, SETI, planetary defense? Does it shift geopolitical priorities, rendering terrestrial conflicts trivial in the face of a larger cosmic context? History suggests otherwise. Humanity has a remarkable capacity to absorb paradigm-shifting discoveries and continue with business as usual. The Copernican revolution displaced Earth from the center of the cosmos, and within a generation, the shock faded into accepted fact. The discovery of exoplanets in the 1990s confirmed that planetary systems are common, billions of them in the galaxy, and public interest peaked briefly before subsiding. Even the detection of biosignatures on another world, should it occur, might generate headlines for a year, and then slip into the background as daily concerns reassert themselves. Extraterrestrial technology might follow the same pattern. Initial excitement, followed by bureaucratic inertia, followed by normalization. But there is a difference between biosignatures and technology. Biosignatures are passive, evidence of life's existence, tantalizing but remote, philosophically significant but practically irrelevant. Technology implies intent, design, capability, potentially communication, potentially threat. A technological object passing through the solar system implies an origin, a purpose, a sender. It raises questions that demand answers. Did they see us? Do they know we are here? Will they return? Should we try to contact them? What would we say? Those questions have no easy answers, no consensus among scientists, policymakers, or the public. The debate over active SETI, whether humanity should transmit deliberate signals into space announcing our presence, has raged for decades without resolution. The discovery of an interstellar probe intensifies that debate. If they sent something here, should we send something back? And to whom? The trajectory of 3I Atlas does not reverse neatly to a single point of origin. The galaxy is in constant motion, stars orbiting the galactic center at different speeds, drifting past each other over millions of years. Tracing the comet's path backward 1 billion years, the uncertainty grows until the source region encompasses thousands of cubic light years. Any response would be a shot in the dark, literally and figuratively. The December 19th JWST observation window is critical. The James Webb Space Telescope, stationed at the Earth-Sun L2 Lagrange point, 1.5 million kilometers from Earth, is the most powerful infrared observatory ever built. Its primary mirror, 6.5 meters in diameter, collects light with an area 6 times that of Hubble's 2.4-meter mirror. Its infrared sensitivity allows it to detect thermal emissions, from objects too cool to glow in visible light, to peer through dust clouds that block optical telescopes, to analyze molecular spectra with unprecedented resolution. When 3I Atlas reaches 1.8 astronomical units from Earth, JWST can point its near-infrared spectrograph at the nucleus and measure the thermal emission spectrum, revealing surface temperature, composition, particle size distribution in the coma. If the nucleus is covered in water ice, the spectrum will show absorption bands at specific wavelengths. If it is covered in organic tholins, carbon-rich polymers formed by ultraviolet radiation on methane and nitrogen ices, the spectrum will differ. If it is covered in metal, the spectrum will be nearly featureless, a smooth thermal continuum determined by temperature alone. JWST's mid-infrared instrument can map the coma's structure, identifying where gas and dust are being emitted, whether from discrete vents or from broad surface areas. It can measure isotopic ratios, the relative abundance of carbon-12 and carbon-13, oxygen-16 and oxygen-18, hydrogen and deuterium, ratios that encode the chemical history of the material, the temperature and pressure conditions under which it formed. Comets from the solar system's Oort cloud show isotopic ratios consistent with formation in the outer solar nebula 4.6 billion years ago. 3I Atlas should show different ratios, reflecting different formation conditions in a different star system. If the ratios match solar system values, the interstellar origin is questionable. The object might be a solar system native on an unusual orbit. If the ratios are wildly anomalous, inconsistent with any known astrophysical environment, the mystery deepens. Hubble, meanwhile, can provide high-resolution optical and ultraviolet imaging. Its cameras, though smaller than JWST's mirror, excel at resolving fine spatial detail. Hubble images of comets have revealed nucleus rotation, jet structures, even surface features on the largest nuclei. Pointed at 3I Atlas in mid-December, Hubble might detect asymmetries in the coma, brightness variations across the nucleus, anything that breaks the perfect symmetry implied by the A3 equals zero trajectory. If the nucleus is a uniform sphere, Hubble will see a featureless disk. If it has craters, ridges, dark patches, light patches, Hubble might resolve them, depending on the nucleus size and Hubble's pointing stability. The combination of JWST's spectroscopy and Hubble's imaging, acquired nearly simultaneously, will provide the most comprehensive dataset on the comet yet obtained. Loeb is banking on that dataset to settle the debate. NASA is more cautious. Agency officials emphasize that JWST time is precious, allocated through competitive proposal processes, peer-reviewed and prioritized based on scientific merit. Observing 3I Atlas is worthwhile, yes, but so are thousands of other potential targets: distant galaxies, exoplanet atmospheres, stellar nurseries, black hole accretion disks. The telescope's schedule is packed for years in advance. Finding a slot for the comet required bumping or rescheduling other observations, a decision not made lightly. The fact that NASA agreed to the observation at all indicates internal recognition that the object is unusual enough to warrant flagship mission attention. But the agency is not preparing the public for a paradigm shift. The messaging remains conservative, framing the observation as routine characterization of an interstellar visitor, not a search for extraterrestrial technology. Loeb is frustrated by what he sees as NASA's risk-averse conservatism, a bias toward conventional explanations and reluctance to seriously consider artificial origins for 3I Atlas. His career of pushing boundaries, arguing that Oumuamua might be a light sail, that some fast radio bursts or techno-signatures could be artificial, has won him both respect and accusations of sensationalism, so his 3I Atlas claims are filtered through that reputation. The anomalies of the comet are real, but their interpretation is contested. This is how science advances, through messy debate and gradual self-correction. Social media, however, skips the nuance. NASA's cautious statements sparked viral memes, NASA cover-up hashtags, and conspiracy theories linking the comet to Nibiru or UAPs. Public voices like Michio Kaku offer more restrained estimates, around 1% chance of artificial origin, arguing that the galaxy's vastness makes probes plausible without letting speculation outrun evidence. Meanwhile, astrophotographers and amateurs produce stunning images that sometimes surpass official visuals, contributing valuable data on jets, tails, and structure. NASA's interactive tools plot the comet's safe, non-threatening trajectory, emphasizing that it will not return. Yet the subtler danger some imagine lies in information. If 3I Atlas were a probe, it might have observed Earth and eventually transmitted what it learned, a scenario speculative but not impossible. Reactions span fascination, skepticism, fear, theological debate, and philosophical arguments over what would count as sufficient evidence for design, with Bayesian priors shaping wildly different probabilities, like Loeb's 40% versus Kaku's 1. The upcoming JWST observations are thus both scientific and cultural. They could reveal clear technosignatures, confirm an exotic but natural comet, or, most frustratingly, leave ambiguity intact. Loeb is pushing hard to avoid that last outcome, arguing for more telescope time and even a rapid intercept mission, though funding and propulsion constraints make it unlikely. As the comet dims and speeds outward, a deadline looms. If decisive data are not gathered soon, 3I Atlas may join Oumuamua and other unresolved phenomena as a permanent cosmic question mark. Its brief passage remembered as a moment when humanity might have learned something profound, and perhaps let it slip away. As the December 19th observation window nears, NASA, JWST, Hubble, ground-based observatories, and even amateurs prepare to capture every photon. The data will be released carefully, balancing the public's urgency with scientific rigor. Those analyzing the observations bear the weight of potentially redefining humanity's place in the universe, ensuring every conclusion withstands scrutiny. Meanwhile, speculation thrives. Perhaps many interstellar objects pass unnoticed, and improved surveys will reveal them. If intelligent life is common, artifacts could drift everywhere, some dormant until they sense a technological civilization. This idea, once purely speculative, now guides new strategies such as interstellar archaeology, searching our own solar system for signs of design. On December 19th, the comet will pass harmlessly, but close enough for detailed inspection. If the results show nothing artificial, attention will shift to the next mystery. But if spectroscopy or imagery reveals something engineered, the paradigm shifts, and 3I Atlas becomes a turning point in human history. The comet remains indifferent, bound only by gravity. When it slips back into interstellar space, it will leave us with data, perhaps clarity, perhaps deeper mystery. If the anomalies persist, the overarching question grows louder. Is this a lone relic or one piece of a larger galactic story? Whatever the answer, the search will continue, driven by the possibility that the universe holds minds beyond our own, and that one of their creations has already passed